We have seen how it is important to define a reference level when we find potential energy, and how it is equally important to know that potential energy is only meaningful when we use it to calculate changes in potential energy and how the change is converted into kinetic energy. Let me now look at what happens when I bring this ball into outer space. So this is Earth. Okay, this is Earth. Okay, now, and I have my little ball. Little ball was here at first, and I can quite happily use the formula mgh to calculate the potential energy when it's close to the surface of the Earth. But what happens now if I take this ball and I take a spaceship and I go very, very far from the Earth? So far that when I look back down on Earth, I see a little sphere, a little bluish sphere of the Earth. So if I'm that far away, I can not use this formula anymore because G is just going to change. But that's not my only problem. I can't use G. Well, G changes, okay, so I can't use the formula. But now H, I might imagine that this distance is the height. H is just this long distance. But it's not so simple. Remember that for H, we need a reference level. Okay, if we are so far from the Earth, where do we choose as the reference level? Now you know Earth. Okay, Earth has lots of mountains. And Earth has mountains, rivers, valleys, ocean, trees, and so on. All sorts of things, all the ups and downs. So where do I take as the level? I mean, if I can take my own the floor in my own house as the level, but that's not very useful because there are all these other people in the world, and we can't actually calculate that very easily if we always have to come back to your room and measure the distance of the ball from the floor in the room. Okay, well, so it's quite tricky to know where to take the reference level is as, and what happens if your house is demolished, and even if you take the top of the mountain, what happens if there's an earthquake and the mountain, the tip of the mountain is blown away and turned into a crater of a volcano? So rather than having to worry about all these complications, there is another place where we can take the reference level. Actually, there are two other places that we can take the reference level, which probably would not change no matter what kind of natural disaster we have. Now, those two places are here. One place is right at the center of the Earth, assuming that we can actually measure a distance from there. Another place is infinity. Okay, the infinity bit is it's a bit tricky, so we'll try to understand that. But first, I'll just say that it is actually there are a few reasons why taking the reference level from the center of the Earth is not so useful. One is that we can't go to the center of the Earth to measure distance from there. There are other clever methods but it could be just be more complicated to actually decide on that. But of course, what about infinity? We can't go there either. Okay, but there's a reason why infinity, we prefer using infinity as the reference level, and it is a mathematical reason. It has to do with defining the way we defined potential energy just now. Okay, I'll call that infinity. Just remind ourselves that it is in a point, galaxy far, far away. Okay, let's review our definition of potential energy. It is the work done to bring a body from a reference point to its position. Right, so let's say the position is here, and I want to bring the ball from a reference point. If I want to bring it from infinity, how can I even calculate anything? Well, that's the mathematical bit. Let's see how it works. I can actually calculate. Funnily enough, I can actually calculate an answer if I bring the ball from infinity. I can actually calculate the work done. Let's see how we can do this. So first of all, to calculate work done, we need to know the force on the ball. Okay, when the ball is here, there is a force. There is a force from the Earth, and the formula for this force, F. I'll write it down here. The formula for this gravitational force F is given by G. G m over r squared. That's the formula, and r is the distance from the center of the Earth to the ball. It's the distance r. Okay, now if I want to find the work done, I must take force times distance. Work done is equal to force times distance. So this is my force, this is the distance. Now clearly, if I take this as the force, okay, and infinity as the distance, I can't calculate anything because infinity is not a number. So what do I multiply? If I take d to be infinity and multiply by the f from there, I'll just get number times infinity, and that's infinity, which is not very useful. But first of all, we have to see that there's a reason that actually we can't do that. We can't just multiply like that, because as the ball moves further away to infinity, or when the ball was at infinity and moving in, the value of the force changes because r changes. So I can't just take the force here and multiply by the distance, because the force is going to be different at different points along the way. So when the force is at infinity, when the ball is at infinity, the force is actually 0 because it's that far away, right? The r goes to infinity at the bottom, so number divided by infinity is 0. So the force there is actually 0, and when I bring the ball in from infinity to here, when I bring the ball all the way in, the force increases. The force increases from 0, and it increases until it is here. So as the force increases, with every little step that I bring the ball in, some work is done, and then that work can be added up to give a final value when the ball reaches here. But it's still not clear how to do it because it's infinity. How do we add everything up, add up all the work done from infinity? Now this is how it's done mathematically. Let me start by sketching a graph of this force. Sketch a graph of this force, vertical axis, horizontal axis. That's the force, that's the R, and that's my graph. Now this is R squared, so as R increases, this answer must decrease. So the graph is going to look like this. It's going to fall, and it's going to be a curve. Okay, and the curve is going to get closer and closer to 0. Now, I need another variable, another vector here to represent distance. I've already called this distance R. So let's say when the ball is on its way from infinity to here, when the ball is there, I need another letter to represent the distance of the ball from the Earth. So let me call the distance here, say R prime. Right, the primed is another way of saying an apostrophe. So the thing there to show that it's a different variable from this. So that's R primed. Okay, so I have my graph. Now, when the ball is at the distance R, let's say R is there, R is somewhere there, distance R. Let's see what it means on the graph when I try to calculate the force. So let's say this at this position, this is a certain position where the distance is R primed. Okay. So at this position, suppose that the ball moves from infinity to here along the way. Let's think about what happens when the ball moves by a small distance. I'll call this small distance delta R. Okay. The delta is a Greek letter, and we often use delta to mean a small change. So over this small distance, called delta R, over this small distance, the force would be almost the same because it's such a small distance. We know that the force increases as we come closer to the Earth, but over a very small distance, the force is almost the same. So if I think about over this small distance, the force is around here. So the force is almost the same. All right. So force here. Now to find the work done at this time during this interval, work done over this small distance, what I can do is I have to take the force and multiply it by the small distance R. The delta R, this small distance moved. If you look at this graph, you see it turns out that force is the height of this narrow rectangle, and delta R, the small distance, is the width or the base of this rectangle. In other words, when I multiply the two numbers, I'm in effect finding the area of this narrow strip here. So that means that this narrow strip of area under this graph gives me the work done over a small distance. And then if I think about what happens when I move it another small distance, in the next smaller distance, the force would have increased by a bit because it is getting a little bit closer to the Earth. So I have a slightly taller rectangle there in a slightly bigger area for the work done in the next interval. Now you can imagine that we can just extend this idea to get lots of little steps, and then I get lots of little strips of rectangle, and eventually I would just fill up this whole area. And if I started from infinity, I can imagine that this area fills up to infinity. Okay, so what this means is that the work done, I can actually calculate the work done if I can calculate the total area in this graph. Now, but that still doesn't seem very useful because I need to add up the area all the way until the graph goes to infinity, right? But surely I should get an infinite answer. My answer should be infinity because the area goes all the way to infinity, so the area should be infinity. It turns out that this graph, this for this formula 1 over r squared, this graph, it comes down to 0 so quickly that after a point, when you add more and more of the area, the amount of new area decreases so rapidly that it hardly adds anything more to the answer. Meaning that if you actually total up all the area all the way to infinity, our answer don't go to infinity, it goes to a finite answer. Now I'm just going to write down the answer directly for this area. The answer for this area is actually G m over r. In other words, it looks almost the same as the formula for f, except that there is no square at the bottom. This is what it looks like. Now, if you have learned some calculus and integration before, right, this is how this is obtained. To obtain this, we need to integrate this function from r to infinity. So what we do is this: we find the area by integrating this formula G m over r squared with respect to r all the way from 0 to infinity, and this gives us the area. And the answer for this integration is just this. So I shan't go into so if you have not learned integration, then don't worry about that, right? In physics, it's fine to accept that this is the answer that corresponds to this area, and someone else has done the mathematics and found that this is the correct formula. So therefore, this is also the work done to bring the ball from all the way from infinity to this point. But that's not the full story yet. There's one loose end we need to tie up. Look at the direction of the force. If you look at the direction of the force is towards the center of the earth. Now, if I'm bringing the ball from infinity to here, then surely I don't have to do any work. Because if you remember, I have, in the definition, in the last session, I've said that this work is the work done by me, or by an observer, by something else, not by the gravity itself, right? By an outside force. It's a work done by an outside force to move the body, say by me to move the body from there to there. So, but I don't have to do any work because the gravity is pulling it towards the earth. So surely I just have to let go of the ball. Okay, maybe if it's at infinity, the force is 0, so I give it a little nudge. The ball slowly drifts and then it goes faster and faster and faster on its own. I don't have to do any work. So why are we talking about the work done? Well, the thing is, the mathematical meaning of this definition is that if you have to push against the work, if let's say the gravity is repelling the ball, trying to push it away, then of course I have to do work to push it back in. But if in this case where the gravity is pulling the ball in, okay, it's fine that I don't have to do any work. But mathematically, we still say that work is done, but we give it a negative value. So that means if it is not me that's doing the work, if it is the gravity that's doing the work, then I give it a negative value. So in my answer, I calculate the work done by the gravity instead of by me, by the gravity. And by giving it a minus answer, I know that I don't have to do the work. It's the gravity that is doing the work in this case. That's one way to look at it. So therefore, what we have seen is that although we have chosen the reference point from infinity, it does not mean that we can't calculate an answer. Right? It's because of the mathematical nature of this formula of Newton's law of gravitation that it depends on 1 over r squared, that the force falls to zero so rapidly that when you go further and further all the way out to infinity, there is actually not much work that is done by the gravity. So that if we think about this problem of bringing a body from infinity all the way to a certain distance r, we can actually calculate a definite answer using mathematics and get a definite formula for the work done to bring the ball from infinity to this distance r. And because of this, because we can get a definite formula, definite answer, it is therefore possible to define the potential energy in this way, to define the gravitational potential energy of a ball using infinity as the reference point. So what this means is that therefore for gravitational potential energy, we would this is more like a general definition of potential energy. So for gravitational potential energy, we would write it this way. Let me just insert some words here. So for gravitational potential energy is the work done to bring a body from, okay, so this time my reference point will be changed from infinity to its position, its as in the body's position.